Welcome students, myself Dr. Shobhit Chattopadhyay from Department of Physics, Shobarani Memorial College, and in this e-module I will discuss over the topic simple harmonic motion. First of all, let us look at a glance what this course will offer you, what quality will be developed after completing this course. After completing the course, you will be able to learn about periodic motion. Also, you will be able to define SHM in terms of various examples. And also, you will be learned about the relationship between uniform circular motion and SHM. To analyze SHM in terms of potential and kinetic energy, you will be able to describe effects of damping, force vibration and resonance, and finally, you will also able to solve quantitative problems involving SHM. Now, what are the challenges for this course? That means, what are the prerequisites of teaching? First of all, you should have primary knowledge on radians, trigonometric functions, and in small angle approximations like sine theta nearly equals to theta when this angle is very small, sine theta nearly equals to theta. This type of small angle approximations is required. Secondly, you should learn to link the kinetic description of SHM with an understanding of how the force changes. And thirdly, you should have a good knowledge on the differentiation of trigonometric functions. So these three are the basic prerequisites for this course. Let us now discuss brief history of this course of SHM. Now, the study of SHM is considered to be started with the experiment of Galileo pendulum. Later, Huygens, Newtons, and others further developed the analysis. Now, there are different kinds of pendulums like clock pendulum, seismometer. These are the examples of pendulums, and all sorts of waves, all vibrations and waves comes under the roof of SHM like sea waves, earthquakes, tides, orbitals of planets and moons, water level in toilets on a windy day, acoustics, AC circuits, electromagnetic waves, vibration of molecular and structural like aircraft fuel stage, musical instrument, bridge, all comes under this study of SHM. Let us first understand what is periodic motion. Now, if the motion of a system repeats itself after a regular interval, this is very important term, regular interval. This regular interval doesn't always mean that the interval in time. It may be interval in space also. So, if the motion of a system repeats itself after a regular interval, then the motion is called periodic motion. So, when we will call it is a periodic motion, if the motion is repeated, it repeats itself after a regular interval time. And this regular interval of time is called period of the motion. It is, I am not saying time period, it is period of motion. Like motion of ceiling fan, motion of arms of clocks, you have seen these motions of pendulum, rocking chair, bouncing ball, vibrating tuning fork. Probably you have seen vibrating tuning fork in your laboratory. Motion of planets or satellites in their orbit. All these are examples of periodic motions. Okay. Now, when the motion is repeat itself as a regular interval of time, then the period of the motion is called time period. This is the most important type of periodic motion when the motion is repeated after a regular interval of time. Now, what is SHM? Simple harmonic motion. First, to learn about SHM, we should learn about oscillation. Now, what is oscillation? Is the to and fro periodic motion is called oscillation. Let's explain it with an example of pendulum. So, this is a pendulum. So, pendulum will oscillate between two extreme points. Drawing is not good, but try to understand it. So, it will move to and fro about this position, say I term is like O, about O. So this type of motion is called vibration or oscillation. Now in vibration always there should be an equilibrium position. Here it is O. So about which the motion will continue. Okay. Now the displacement of vibrating or oscillating particle is measured from the equilibrium position. So distance traveled by this particle from this mean position is called displacement of the particle. Okay. Distance traveled from this equilibrium position, such a specific instant of time, what is the distance of the particle from its equilibrium position, that is its displacement at that time. Now if the acceleration of the vibrating or oscillating particle and hence the force, that means acceleration or force, we know from Newton's law that force is equal to mass into acceleration. So we are saying accelerations are hence force acting is proportional to the displacement. So when acceleration or force is proportional to the displacement and always directed towards the equilibrium position, then the motion is called simple harmonic motion or SHM. So one thing we can say here, that all SHMs are periodic, but all periodic motions are not SHM. That means periodic motion is a set and SHM is a subset under this set. Okay. Now if F is the force on the oscillating particle and X is the displacement from the equilibrium of the mean position, then the motion will be SHM if force is directly proportional to minus x or force is equals to minus kx. Okay. Now where this k is termed as force constant, sometimes it is also called spring constant when we will consider the vibration of spring. Okay. And the negative sign on the force indicates that it is a restoring force. Restoring force means it is directed to restore the mass to its equilibrium position. So it is always directed towards the equilibrium position. Okay. Now there are few important terms we need to know in SHM. First of all, the mean or equilibrium position, already I have discussed about it, the point where the oscillating particle will remain in equilibrium. Just in case of oscillating pendulum, this is the middle position is the equilibrium position. Middle position is the equilibrium position. Okay. Next, displacement. It is the distance, say at any instant of time the pendulum is at this position. So the distance of this pendulum from this mean position, say this is at A position. So distance of A from O is called displacement of the particle. Okay, distance of A, and it is symbolized by x. In both sides you will get displacement. So this is B. So this is called displacement. Then come amplitude. When the displacement is maximum, that means when it reaches its highest point, then the displacement will be maximum, that is called amplitude. The maximum displacement the maximum distance covered by an oscillating particle on either side of its mean position. It may be on left side or on right side. On either side, then it is called amplitude. So amplitude A is equals to maximum x. Then comes time period. Time period also we have also discussed it earlier, that it is the time taken to complete one cycle of its oscillation. One cycle means, again, let's draw that pendulum. These are two extreme points. First, it started in this direction from O, reaches A, then return back to O, then goes to B, and again return back to O. So when it returns back to O, it will be at the same position when it has started, because at the starting moment it is going towards A, and when it is returning from B, it is again going towards A. So this is a complete cycle, going from O to A, then A to O, O to B, then B to A. This is a one complete cycle. So time required to finish this complete cycle is called time period. Then comes frequency. There is a simple relation between time period and frequency. Actually, total number of complete oscillation in unit time interval is called frequency. It is symbolized by F. Time period is symbolized by capital T. So this capital T is equals to 1 by F. So it is inversely related. Time period and frequency are inversely related. Next comes phase. This is also important. It is the argument of the trigonometric function that represents SHM. We will represent SHM by some y equals to a sine omega t plus phi. This term within the bracket omega t plus phi, this is the argument of the trigonometric function, and this gives equally this term actually gives you the position, exact positions and state of motion of the oscillating particle. Okay, position, velocity, acceleration, all. So this is called phase. This is also very important term for understanding SHM properly. Now let us relate SHM with uniform circular motions. Look at the picture. Here a particle is moving in a circular path and its projection on one of the diameter will move like SHM, as if it is performing SHM. Okay. So let us consider the uniform circular motions of a particle. The motion of the projection on x or y axis will be SHM. We will prove that. Let us consider A is the radius of the circular path. A is the radius of the circular path. A is the radius of the circular path, and theta is the angular displacement. So they have started from this position, say this position, and the particle goes up to this position. So the radius is A and theta is the angular displacement. Then the displacement of the projection from this O point, this will be the mean position on the x or y axis, will be given from the center of the circle is either x equals to A cos theta, or if we look into along y direction, it will be A sin theta, where A, which is the radius of the circle, will be treated as the amplitude, that means maximum displacement from the center. Okay. Now, if omega is the uniform angular velocity, the particle is moving with uniform angular velocity. If omega is the uniform angular velocity, and after time t, if this reaches this point, then theta equals to omega t. Theta equals to omega t. This theta equals to omega t. So we can write x equals to a cos omega t. So velocity will be dx dt, which is equals to minus a omega sin omega t, to minus a omega sin theta, and acceleration is dv dt equals to minus a omega square cos omega t, or minus omega square x. So you can see that acceleration is proportional to minus x, which is the essential criteria for SHM. So the motion of the projection is SHM. Okay. So whenever there is a uniform circular motion of a particle, then the projection of that particle or on any of the diameter will be a SHM. So this is the relationship between uniform circular motion and SHM. Now let us discuss about the energy of SHM. The total energy of SHM is comprised of two components. One is kinetic energy and other is potential energy. Now first let us discuss about kinetic energy. K is equals to half mv square. So as we know, x equals to a cos omega t. So we can calculate v, which is equals to dv dx, which is equals to minus a omega sin omega t. So k equals to half mv square, half m into minus a omega sin omega t whole square. This is equals to half m a square omega square sin square omega t. Now sin square omega t can be written as this. If I look into the previous slide, then you can see from this figure, this is a, this is x. So this distance is root over a square minus x square. This distance, vertical distance. So cos theta can be written as cos omega t is equals to x by a. So if you put the value, you will get k equals to half m omega square a square minus x square, or half k a square minus x square. Okay, where m omega square is considered as a constant, small k, that's force constant. When x equals to 0, k is maximum, and this value is half k a square. And when x equals to a, that is amplitude, k is minimum, kinetic energy is minimum, k min, and the value is big 0. If you put x equals to a, it will become 0. So kinetic energy is maximum when displacement is 0, that means when the particle is at its equilibrium position, and kinetic energy is 0 when the particle reaches at its extreme point. Next comes to potential energy. For that we start from the force equals to minus kx. So for small displacement dx, the work done will be minus f dx or plus kx dx. So total work done for the displacement from 0 to x will be half kx square, and this work done will be stored at potential energy of the oscillator. So the potential energy is half kx square. So when x equals to a, potential energy is maximum and is equals to half Ka square. Again, if we see what happened, just a minute. If we take x equals to 0, that means at equilibrium position U is minimum and which is equals to 0, U is 0. So the total energy is sum of the kinetic energy, potential energy, and it is equals to half Kx square, which is equals to either maximum kinetic energy or maximum potential energy. Now look into the graphical relationship. This solid line describes the variation of potential energy and the dotted line describes the variation of kinetic energy. At the two extreme ends, kinetic energy will be 0 and potential energy will be maximum. And at equilibrium position, potential energy will be 0 and kinetic energy will be maximum. Okay, and the total energy will given by this black line, it will remain constant throughout this motion. Now let us discuss a little bit about damped harmonic motion. So it is a harmonic motion with some damping force like frictional or drag forces. And if the damping is small, we can treat it as an envelope that modifies an undamped oscillation like this. Here you can see the frequency of undamped oscillations will remain unchanged, but its amplitude will decrease with time, and at a point it will become 0. So oscillation will die down. Now if the damping is large, it no longer resembles SHM at all, and you can see this curve A gives you the underdamped motions where there is a little bit of oscillations that will die down with time. Curve B will give you critically damped. Here it is the fastest way to go back to its equilibrium position, and C is the overdamped. It will, if we displace it from the equilibrium position, then the particle will slowly move to the equilibrium position, very slowly. It is called overdamped. Okay. Now there are systems where damping is unwanted, such as clocks or watches, but there are systems in which damping is wanted and often needs to be close to critical damping as possible, such as automobile shock absorber, earthquake protection for building. Like these are some pictures from shock absorbers for this is for automobiles, this is for building protection. Okay, next move into the force oscillation. Now when damping is there, what will happen? The oscillation will die down, but we in actual case always there is some damping, so all the oscillations will die down. But if we need some sustained oscillation, then we have to overcome the damping. That means the energy which is lost to overcome the damping force, and we need to supply some energy from outside by giving some periodic external periodic force. Okay, and force vibration occurs when there is a periodic rising force. This force may or may not be the same period as the natural frequency of the system. It may be at par with the natural frequency of the system, may not be. But whenever the external force is there, external periodic force, the system in steady state will oscillate with the period or the frequency of the applied force. So if the frequency is same with the natural frequency, then the amplitude will be quite large, and that is called resonance. Now see, this is when the frequency matches with the natural frequency, this we will get some peak of the amplitude. The amplitude will be very large, otherwise the amplitude will be smaller. And when this amplitude will be very large, we call it as a resonance. Now you can see from the graph here this resonance is very sharp, but here it is a flattened resonance, flat resonance. So the sharpness of resonance peak depends on the damping. If the damping is small, it is quite sharp. If the damping is large, then it is less sharp. Like damping, resonance can be wanted or unwanted. Musical instrument and TV radio receiver depends on it. Okay, what is its actual application? Now I will supply some numerical problem sheet along with this video lecture. You should consult those numerical problems, and I think you will be able to do those problems. Thanking you at the end.